Dear students, today we shall be discussing about diffraction at a straight edge. Imagine we have a source of light here. It is illuminating a slit, and this slit is further acting as a source of light for an obstacle. Say this is an obstacle, and we have a screen that is placed here. Remember, this is an example of Fresnel type of diffraction. Fresnel type of diffraction, in which I have already told you that the source of light, the slit, and the screen are at a finite distance from each other. Therefore, we don't need to place any convex lenses or collimating lenses in between, right? Now, let us see what happens. So, this is a ray of light which goes and hits the screen straight. At this edge, there can be a ray of light which can bend on account of diffraction, and from here there is another ray of light which meets the screen directly at this point. Now suppose the central point is O and this point is O dash. The distance between them is x. Let the distance of the obstacle from the screen be b, right? And then we can also imagine a wavefront like this. Suppose the radius of the wavefront is a, it's a. Let's name these 2 points as A and B, right? Now, if we want to find out what is the intensity pattern on the screen due to this diffraction, we need to find out, as always, the path difference between the rays OB and OA. So what are we essentially interested in is path difference. Path difference equal to O dash B minus O dash A. Now what is this O dash B? This can be found from this triangle. So O dash B is under root b square plus x square. So b will be taken common. You are left with 1 by 1 plus x square by b square. And then when you expand it binomially, this is b times 1 plus half of x square by b square. The power comes down and the higher terms are neglected, right? So then you multiply this b inside, it is b plus half of x square by b. So this is O dash b. Now we are interested to find out what is O dash a. What is O dash a? This O dash a can be found out like this, that it is SO dash minus SA. So O dash a is SO dash minus SA. And what is SO dash? SO dash, the base will be a plus b and the perpendicular will be x. So it will be a plus b square plus x square. A plus b will be taken common. You are left with 1 plus x square by a plus b square over 1 by 2. Then we will expand it binomially, right? So this is a plus b, 1 plus 1 by 2 x square by, and the higher powers will be neglected. Then you multiply this a plus b inside. So it is a plus b plus half of x square by a plus b. One of this will get cancelled with this, right? But you are actually interested in O dash a. So that O dash a is basically SO dash this much minus SA. And what is SA from the diagram? It is a, small a, right? So this is a plus b plus half of x square by a plus b minus a. This a and a will go. You are left with b plus half of x square by a plus b. Now we have obtained the path difference. We know that path difference was equal to this, that is O dash b and O dash a minus O dash a. So what was O dash b? It was b plus half of x square by b. And what is this O dash a? We have found it out, that is b plus half of, that is b half of x square by a plus b. So this b and b will cancel. Path difference will be how much? This will be half of x square will also be taken as common. We will be left with 1 by b minus 1 by a plus b. So this is x square by 2, a plus b minus b by a plus b. So this and this will go. This is x square a by twice a plus b, right? So this is the path difference. Now we set the conditions for maxima and minima. And what are those? We know that for diffraction from a single slit, the conditions of maxima and minima based on your previous knowledge is that if this path difference x square a by 2 times a plus b is equal to 2n plus 1 lambda by 2, it is the condition for maxima. And if this path difference is equal to n lambda, this is the condition for minima. So this is the condition for maxima and this is the condition for minima. Now remember, in case of maxima, n can be given value equal to 0 because we know that in case of diffraction the central fringe is always bright. So n equal to 0 is actually meant for the central bright fringe. And in case of minima, we can start giving values to n from 1, 2, 3 and onwards, right? Now let us give the value to this maxima for the two extremes, that is the first bright and the last bright. So for the first bright, n will be equal to 0, right? So what is this? X square a by twice a plus b. This will be equal to lambda by 2 only, right? So 2 and 2 will go. What is x naught? X naught, because we have given value 0 to n. So this x naught is how much? A plus b lambda times by a under root, right? And the nth value of x, from this expression can be obtained as xn is how much? It is a plus b lambda times by a 2n plus 1 under root. From here, if we are interested in finding out what is the distance between the two brights, that will be xn minus x naught. And how much is that? That is obviously a plus b lambda times by a, and then we can take this factor minus 1, right? So what is the importance of this expression is that you can find the wavelength of the source of light that you have used at the initial place. And how do you do that? Because in the experimental arrangement, you know what is A, you know what is B. You also know what is the distance between the first bright and the last bright. So from the experimental setup, you are able to determine what is A, what is B, what is the distance between two bright fringes on the screen. Therefore, once you know all those parameters, you can easily find out what is the wavelength of the source that you have used at the first place, right? Now, the question is that what will the intensity pattern look like? Now, again, if you go back to the experimental setup, we know that this portion is geometrical shadow. But on account of diffraction, some light will also penetrate in this region, right? And you will be obtaining diffraction pattern on the other side of O, from O to O dash and onwards. So when you draw that, it will be like this. So it will be like this. Suppose this is O and this is O dash, right? So we know that beyond O, this is geometrical shadow, GS. So there is some portion that will penetrate this region, and this is the peak, and then we have subsequent peaks. It will be like this, right? Now, using the same concept, we can also find what should be the diffraction pattern, or what should be the intensity pattern due to a wire. Now, the wire can further be classified into two. One is a thin wire and another is a thick wire. Another is a thick wire. Now, in case of thin wire, what should happen? If you have a thin wire, its edges are also very sharp, like the tip of this pen, right? Since they are point sources, they will act as coherent sources. So on the screen, you will be obtaining a diffraction pattern on this side, a diffraction pattern on this side, because you can treat this arrangement like the diffraction at two edges. Remember, in this case, this is a diffraction due to one edge only. But in case of a wire, a thin wire, the 2 points on the wire can act as two edges, right? So you will have a diffraction pattern on this side and a diffraction pattern on this side. But since these are acting as point sources, these are coherent. They will also produce an interference pattern in this region. So a ray of light bending in this way and a ray of light bending in this way. Since they have same path length, the path difference is 0. This will be a constructive interference at the center. And at all other points, you will have to determine whether the path difference is n lambda or 2n plus 1 lambda by 2. Accordingly, you can say whether it will be a bright spot or a dark spot. But in this region, you will be able to find out an interference pattern. And beyond these two edges, you will be able to get a diffraction pattern, right? So the intensity can be traced like this. Suppose this point is O and the point in line with this edge is O dash. So between O and O dash, you actually have an interference pattern. And in case of interference, we know that the intensities of bright fringes are equal. They will be shown by a graph of same height. But beyond this, it is a case of diffraction due to an edge. And here, this is also a diffraction due to an edge. And the graph will be like that, what we have shown earlier. Right? The rest of the mathematical description will essentially remain the same. Now, in case of thick wire, that is when the diameter of the wire is relatively large, what will happen? That both the ends of the wire will still act as edges. They will act as edges. And we will have a diffraction pattern on the screen due to this edge and due to this edge. But because these are not point sources now anymore, so they will not be coherent. So we will not have any interference pattern in the center, right? Since these are not point sources, because the diameter is relatively large at this time, therefore these two sources will not act as coherent sources and we will not have any interference pattern in this region. But since these act as edges and the diffraction pattern due to these edges will still be visible on the upper and lower side of the screen. So what will the graph look like? So you have a point O and O dash. Of course, they are the points in line with the two edges. What do you expect? On this side, you have a diffraction pattern like this. And on this side, you have a diffraction pattern like this. But in the center, you don't have anything. And even if you have, that will be very feeble. Very feeble. So this is how we can also explain the diffraction due to a wire, a thin wire and a thick wire, by extending the concept of straight edge, diffraction due to straight edge to this. So I hope that gives you a fair idea of diffraction at a straight edge, and further extending the same concept to explain the diffraction due to a wire, which can be a thin wire or a thick wire. The mathematical description essentially remains the same. There are certain details that change that I have told you. What kind of details change? So I think that's all about this topic.